So today we're going to talk about convolution neural network. This is the second architectures that is being very popularly used in neural network. So let's just talk and look at this MNIST data set. So we have been, surely you guys have been using this for a lot of time. So basically, we have 60,000 training data set with 10 labels and a 10,000 testing data set. So this is basically you build your models on this 60,000 training data set. And each label has about 6,000 data set. Every label have equally distributed data set. So there's no and data imbalanced so issue. All the data is balanced, and then you have 10,000 testing data set. So here is the accuracy of the MNIST data set in general. So for the linear classifier, if you're just using say logistic regression, you're getting 12% of error in general. And SVM, you can get error of 1.4%, which is really, really good. The best SVM result, and you can get is 0.56%. However, you can, using neural network, you can build a bunch of neural networks. For example, the two-layer neural network, which is just slightly like two hidden layers, and 3 layers neural networks is like 3 hidden layers. It gets about 2.5%. For CNN convolution neural network that I'm going to talk about today, it's one of the one. It's called LaNet. You can get 0.85%, which is really good. Compared to the best SVM, result you can get it. This is almost equivalent. However, if you get larger convolution neural network, in the last like 10 and more than 10 years ago, you can get 0.3%, which is really, really good. 0.3%. This is almost like human level of accuracies. So basically, MNIST digits is like that data set is done. So basically, nobody is using this data set for any kind of challenges because this is so easy. 10 years ago, people start to work on like much more challenged data set. For example, this is called ImageNet. So this is much more complicated data set. It has actually 1.2 color images. Each image has 256 by 256 for training and 100K for testings. And that turns out that object classes is more, about like 1,000. So this is much more complicated and much more difficult and a data set to work with. For example, right here you have the mammal, you have a dog, so you have a walking dog, you have a husky, you have all different things, right? And also they have a different categories, and these like categories is also being like included. It's like and you have a larger categories of mammals, then you have gradually going down to the dogs, and then working dog, and then huskies, right? So and husky is the smallest thing, and the classes that you can get, but. For the huskies, and they also belong to each of the categories right here. And the same here, you have a like vehicle, you have craft, watercraft, and so on. So and each classes are not like independent with each other's like MNIST data set. In fact, they are, and it can be like inclusive, right? So and one class is completely included in the other classes. So this is totally possible. So these classes, object classes, are much more complicated, And the model is getting deeper and larger, it's more complicated. And also the point is those computational for large scale networks are usually made parallelizable by using GPUs, which is very essential part in deep learning revolutions. In fact, in this course, so I'm going to show you how to tune those neural networks with the GPUs and so on. Okay, so, and this is very important. And you can see right here, and this is give you some like image net challenge. So just a second. Okay, so, and you can see this is the winner of the ImageNet challenges test era. If you're using shallow neural network, you're getting about like 75% of accuracy, which is okay, but it's not like the most impressive. But you're getting like 8 layers of neural network. You're getting start to have like something called AlexNet, which is about more than 10 years ago. You're getting like an 85 and 80% accuracies. Now you have like evolve those neural networks architectures to VGG, GoogleNet, and ResNet, right? So ResNet is being proposed in 2015, which is a like staggering 152 layers. You have 60 million parameters to learn, and the whole like ResNet, it has like 224 megabytes memories to store into the GPU, which is quite big at that time, and you can do and like 11.3 gigaflops per predictions. So, but the accuracy you can get is almost like 96 and 97% of accuracy. So this is already reached the superhuman position. If you let a human to do any kind of predictions, you can only get about 95% of accuracies. So one of the thing is, before that, and before the AlexNet, these like neural networks is not doing very good job. In fact, this is like fully connected neural network, which is MLP, doesn't work very well for those computer vision applications. One of the reason is it has too many parameters and it's very hard to train. So it has very poor performances. I'm going to show you, I'm a little bit later with the code as a comparison that if you're using like convolution neural network, in fact, you only have a very few parameters compared to if you're using fully connected and a network. Because if you have fully connected networks, each neural like nearby layers, they are always fully connected. You are learning a lot of parameters in this situation. For example, right here, so for example, this is some idea of like a structure of VGG. So the input is 224 by 224 by 3. 3 means I have 3 channels, and which is RGB channel of the images. I'm going to tell you things like a little bit later. But let's see, like just for the first layers, we are transforming the 224 by 224 by 3. Then like say this is the first layer, it's 224 by 224 by 64, just for one passings, just one passing from first layer to and from input to the first layers. Then the input dimension, and this is input dimension, this is output and the dimensions. Just for that single one, then the number of parameter, if we're using fully connected, that would be 483 billion parameters. And this one, this is impossible to train, okay? Because this is way too many parameters. Nowadays, even with the ChatGPT, this is like say with this like and the certain levels of the and the ChatGPT and others, that's about like 100 billion parameters roughly, right? That's the maximum we can train at this point. But if we're using fully connected just for one layer, that's already more than the number of parameters that we can train right here. So this is basically stupid that we cannot do it. And also there are also very important, informations that we want to talk about in the convolution neural network is, first thing is it has a local connectivities. And the second thing is called parameter sharing. Okay, so this is very important. And this is everything in the convolutions. Also, there will be something on the pooling. The pooling, it actually can reduce the size of the representation. It can also do some downsampling as well. So like to shrink the size a little bit smaller. First thing first, so let's talk about convolutional layer, because this is called convolutional neural network. So this is, of course, has something, about the convolutional layers. First thing, convolutional layer is still a linear layer, right? Like think about it, fully connected. Before you apply any activation functions, this is always a linear layer. It's a basically think about a matrix multiply on the input. So and the same as like convolutional layer, this is a linear layer. What it did is basically take the image of features output from the hidden layers as input in the original shape without any vectorization. So that means I didn't reshape anything, just take as 224 by 224 by 3. So this is basically my input, which is like you can think about as a tensor or like or like three-dimensional array, right? So this is actually a three-dimensional array. So why this is important rather than you do any kind of like a reshaping to a vector? The reason is each image has its spatial information. So basically, if you look the nearby pixels, they are highly correlated, right? So this is basic means I need to capture certain like spatial informations of the images when we process these data. These neighbor and pixels will help us to understand a lot of information. And also, we are trying to train a weight that is actually a 3D or 4D tensors. I'm going to call it filters. It's basically filters with maybe 3 channels or 4 channels, depends on what you're going to work with. The weights training and the local sparse connectivities versus the full connectivities in the dense layer. So basically, I'm going to using the same filter and apply on the images. So this will be also my and work on this local connectivities. I'm only interested in the and the local regions of the images. It's much more compact in terms of model size because it turns out we have less parameters in this cases. So what is the local connectivities? It basically says I'm only in, and each hidden unit is connected only to subregions of input. And also connected to all the channels RGB. So basically, when we trying to apply this convolutional and a layer, in this case, is only interested in the like subregions of images, right? So you think about, and this is what we got for the fully connected cases. So that means this neuron take informations for every images from the and from the each pixels. But on the contrary, what we have for the convolution neural networks is, for example, this neuron, I'm only taking the information in these regions. So that means it only focus on the regions that is up and upright corners, right? So this actually can capture well for those subregions and they give us some like good spatial informations. Same here, you have like RGB, you have a red, you have green, and you have blue, and so on. So these are also very and important information on different channels, because sometimes different data has an image has different and a different channel can give you a different informations basically. And also these parameter sharing, that means I'm making a very reasonable assumption that if one feature is useful to compute some spatial position of X and Y, it should be useful to compute at different positions. So that means these parameters, if I'm focusing on the up right corners for those parameters, they should also have the same parameters if I'm interested in, say, and up left corners, right? So I'm going to using exactly the same parameters to process each sub-regions of the images. Right? So this is a good assumption, because if this is useful in that specific region, it should be also useful to process in the other regions. So first thing is we need to do is this convolution operators. What is this convolution operator? So this is basically the definitions, right? So what you actually think about is you put this like matrix, and this is 3 by 3 matrix. This is 2 by 2, and you think about this is my image of X. This is my kernel of K. All right. So basically, is this matrix? You element-wise and multiply this matrix together, then sum them and together. So basically, you think about this is you overlay these kernels on this upper left part, and a corresponding entry, they multiply them together, then they sum together. You get 1.15. Then you move one step from here into the and this corners, right? So this is, you do the same operations, you entry-wise multiply them together, then sum them together. You are getting 4.5. So then you process this is each of this. For this specific cases, since my image is 3 by 3, my kernel is 2 by 2, you end with getting a 2 by 2 matrix. So this is what you got after you process this convolution operators. And I want to emphasize this convolution operators is actually linear. Okay, so it's always linear here. Okay. So first thing is this 2D convolution just basically works for matrix input. I'm not going to reshape into a vector or an array. I just input as a matrix or tensor. I directly and apply this kernel on that. So this is one convolution kernels, a size of 2 by 2, transform 3 by 3 input as a 2 by 2 output. However, if you want to do a dense layer instead, my input is 9, like basically 9 neurons, and my output is basically 4 neurons. 9 times 4, that would be 36, right? So basically we have a 36 waiting to be learned. However, if we're using like convolutional operators, the only thing that we actually need to learn is that kernel, which is 2 by 2. I only have 4 parameters, 4 weights need to be learned. So this is, like you can see, this is significantly, number of weight is significantly smaller. And also you can have a bias if you want, but usually we don't have. And we could have a multiple kernels of 2 by 2. So you can think about it's multiple channels. And for example, if we have, and for 4 filters, and then what we got is 4 by 2 by 2. So basically, you can think about you stack these two and the 2 by 2 filters together. You have 4 different filters. You stack them together, then you're getting 4 by 2 by 2 tensors. That will be the output. Okay, so you can also make different choices like 3 by 3, 5 by 3, 5, or 7 by 7. So this is basically think about as a and you can like directly think about this local connectivity and the parameter sharing. So basically, I only care about these 2 by 2 regions or 3 by 3 regions, depends how large the filter that we want to do. So basically, you can think about I'm going to learn maybe 4 filters, and each filter is 2 by 2. So I mean, total we only have a 4 times 2 times 2. That's only 16 weight. This can already capture a very good amount of information of these images could have. All right. So let me just take one simple examples, and in fact, this is just a very simple examples that we can use. And I want to emphasize the D. So the input is 3 by D by D. D by D is the number of pixels of the images, and the 3 is, that means I have a 3 channel, which is RGB channels. Here I'm going to using filter size is, I have the kernel size is 3 by 3. I'm taking 3 filters. So like 3 filters, each filter, the kernel, and each kernel has a 3 by 3 size. So that in total that we want to learn is 3 by 3 by 3. And the stride is equal to 1. So that means at each time I'm only going to move that kernel for 1 step, right? Just from here to just 1 step. So what we do here, and also the output size is D and a D minus 2 times D minus 2. And of course we have 3 and the 3 channels, right? So, and that means we have to process the RGB in a different ways. So basically, and the output should be like and the 3 by D minus 2 times D minus 2. But you can see right here, we already have a problem is this convolution can reduce the image dimension. So if we have a multiple layers of convolutions, then this dimension will getting smaller and smaller. So this is, and this could be a problem. So that's why we need to handle this a little bit later. So you can think right here, for example, if this is my kernel channel 1, this is kernel channel 2, and this is kernel channel 3. Oh, so and also so once they have like 3 channels, I'm going to add them together. So like, and that's why they don't have like 3 times like D minus times D minus. It should be just D minus 2 times D minus, because I'm going to add these I mean information of these 3 channels together. And of course we can add a bias if you want. So what you actually do is say if this is my kernel channel number 1, this is kernel channel number 2, this is kernel channel number 3, it actually multiply these regions of the matrices for the RGBs, and element-wise then sum them together, right? So you get 308 minus 498 plus 164 plus 1 is the bias, then the output is minus 25. Okay, so then what you do is you move this kernel channel by strike 1. So that means I'm only going to move these things 1 step to the right. You're getting this, and getting this. So then you apply this kernel and the kernel channels again, you're getting this output 466. Okay, so and then you're going to strike by 1 again, so this will be right here. So you basically gradually moving your matrix 1 by 1. Okay, just 1 step by 1 step, because my stride that I define is actually equal to 1. Okay, So this is like how you actually create this output matrix is right here. So this is you do it one by one. But of course, you can see right here, as I said, that the output size is actually shrinked from d by d into d minus 2 by d minus 2, which is not really ideal. So if we apply this like convolution layers and again, it actually will create a problem that my size is getting smaller and smaller. So what we can do to avoid this is we can do something like zero padding. Like zero padding actually can allow to go over these boundaries. So it can easily control the size of output layers. So the dimension of input output will be the same if we padding the zeros around this, right? So if say if we have a 5 by 5 matrix, I'm going to pad a bunch of zeros around that and to make a 7 by 7 matrices. Then after this kernel, this is will still be 5 by 5, right? So and the difference is, the key point is actually once you apply this kernel, you're starting with the left upper corners. Then you just stripe by 1. You will find out, and as I'm not getting d minus 2 by d minus 2, instead I will actually get it for d by d matrices. So this is zero padding is very important in order to make sure the input and output have the same amount of the dimensions. Both will be d by d. Okay, so for 3D input to the convolutional layer, so this is slightly more complicated, but instead of you have like kernel being like a matrix, it actually the kernel will just being a tensor. So basically you are going to like convolute this dimension d, w with width, and h is height input features with d out of filter size of the same and the same like dimension times the kernels and the dimension stripe by 1. So basically right here, you can think about this is the dimension is equal to 3, but the kernel is actually dimension is 3. So basically you are getting 3 by 3 by 3 size of filters, and say you have a d out number of filters, right? So you say you have like different and the numbers of filters here. So here and right here you can see this is and this is the filter size is 3 of that, and you have this is being the red channel, green channel, and the blue channels. It actually sums them together. So and it becomes like and it becomes back to be the matrix again. Here, if we treat everything into 3D input, and you can just using a tensor as like 3-dimensional tensor as the way to convolute the input. And we still have the issue that the output dimension is like shrinked. It's just because of the same reasons. So that's why the like zero padding is important even for the 3D input as well. So this is also important. So you can pad zeros around this like in the 3D tensors. All right, so and also there's another layer is also very important. It's called pooling layer. So it's very important to insert some like pooling layers in between of successive convolution layers. So pooling layers can reduce this like spatial sizes to reduce the amount of like parameters. It basically says just basically operate each features independently. So and a way of thinking is and sometimes we do want to shrink dimension a little bit less. And smaller is very important because we cannot approximate this data with that many of the dimensions. So we need to do some like downsampling. So like pooling is basically, think about it, it's like downsampling. And for example, the one of the popular one is called max pooling. Max pooling is 2 by 2 max pooling with, and usually like stripe by 2. It's I mean, it's commonly used here. So by pooling, we actually gain some robustness of the like, and what is like spatial location features. So basically, this is the matrix that we're getting here. I'm going to apply the max pooling with the 2 by 2 filters. So that means I'm only extract this maximum values for each block of 2 by 2s. So for this 2 by 2, I'm going to take the 6. I will take stripe by 2 set. So that means I'm going to skip into the matrix of the green, that I'm going to take the 8. So you think about everything being like downsamplings. I'm only interested in the maximum value because we know the maximum value is the most important part. So that's why this is like maximum pool is very, very popular in the convolutional neural network. And you can think about this is my image of 224, and by 224, it actually downsamples to 112 to 112. So basically, we just take the maximum values of the nearby pixels to shrink these images by 4. Okay, and think about it like this. So basically, this is the convolution layers. So this is 3 by 3 convolutional layers. It actually will get and we'll get like values and so basically this is the, and the 3 by 3 is, and after you apply the convolutional layers, and this is the like, and the little regions right here will be output, and that will be the value for this little neurons after we apply this convolutional layer. So you're getting 3 by 3, but actually if we're taking this max poolings, so that means I'm only getting the information of the maximum value of this 3 by 3 matrix. Every others, I'm going to throw them away. Sometimes we're also using average pooling as well. This is also commonly used. And also we need to and apply this as fully connected layer. Sometimes it's often used in the last layer to map these image features into predictions. So basically, this convolution neural and a convolution layer and also max pooling layer, we are trying to extract the features of the images, right? So it's kind of like we only have an image to start with, but those pixel values are really terrible ways to represent those features. The best way to represent the features is actually we extracting those local informations around these images. So this is exactly this convolution neural network is doing. But after that, we still need to make some predictions. For example, we need to predict whether this is a cat or dog. So that means we actually still need to kind of perform like and MLP. So that was usually as the last layer, we are going to map this and image features to our predictions. At this point, we don't have any spatial information because it's already embedded in the image features. In this cases, it would be inefficient because we have a lot of weight and we don't have any weight sharing. So that's why we're trying to minimize the number of connected layers. We're only using connected layers at the end. So when we already shrink our dimensions to much smaller, and such that those connected layers don't have a lot of weights need to be worried about. So if we look at this VGG right here, you see like these, from this to this like and black, they are all convolutional layers, and this red is actually max pooling. For the max pooling, it actually shrink the dimensions, like intentionally, by like extract the most important part. But if we look this whole thing right here, we're only using the fully connected at the very end, right here, and at the end we apply the softmax. So basically, right, and that's the places actually we are using those neural networks, like NMLP, like neural network architectures. Everything above right here, we are still, and we're using convolution layers and the max pooling layers. Right? So up to this, we are still trying to extract the informations or like features of images. I'm trying to transforming this features of images. And then I'm going to plug into this MLP such that I'm training my MLP to get my and predictions as accurate as possible. Same here. So this is one of the popular like architecture, which is LaNet. It's basically you do convolutions, then you have and then you get like 28 by 28 and then you have a 6 and the 6 filters need to be processed. Then we do the subsampling, which is like poolings. Then you got like 6 to like 14 by 14. You just like and a max pooling of 2 by 2. And then from here to here, you're still doing the convolutions. This convolutions again, but you are going to apply 16 at 10 by 10. So you have like 16 different filters, right? So, and in convolution and a layer, we usually just don't and apply one filter. We usually apply 16 or like and 2 to the nth numbers of the filters. Then we do the subsampling. Then we do the as at the end we are getting and we are getting the and the 16 and the 16 filters, and each filter is and so each layer there will be 5 by 5. So then we are going to apply this for the connections for 3 layers. So sorry, for 2 layers, and this one is 120 neurons, and the next will be 84 and the neurons, and output will be 10 because we are trying to do the MNIST data set. Okay. All right. So, and also they have other tricks. For example, the Gaussian connection. So that means this is some has some like dropouts and going on here. Okay. So basically, what is, I mean, this is what we are trying to do here. So and we pad image with the zeros and increase the size to and 32 by 32. So then we are getting the like MNIST data set. The first one is convolution and a neural network. Convolution layers 1, the 6 filters, and each filter is 5 by 5, and I'm going to apply this like stripe by 1. After this convolution layers, I'm going to follow by the sigmoid activations. So basically, each entries element-wise, I'm going to apply the sigmoid and a sigmoid and functions, and so like sigmoid like activation functions. So as a result, you are getting four filters, and each of that will be 28 by 28. Then I'm going to apply the max poolings, and as I said, to shrink this by half. So as a result, you are getting 6 or 14 by 14 maps. And then I'm going to apply the second convolution layers, which is 15 filters, and each filter is 5 by 5 and stripe by 1. After that, I'm going to apply the sigmoid activation again. As a result, we are getting 16 different 10 by 10 maps. Then we do this max pooling one more time. Then you are getting 16 and different 5 by 5 maps total, and we are getting 16 times 25. So we have 400 values. So these 400 values you can think about as the features of the images, right? So I'm instead of to work on the image directly, I'm using those kind of convolution layers to actually to extract this 400 different features. Then I'm going to apply this like 3 fully connected layers, also 120 and 84 and so on. And they all have the sigmoid activations. At the end, you have a 10 neurons and followed by the softmax to make sure you actually output the probabilities. In total, this is about 61,000 trainable parameters. You can get the accuracy on the tested data for 99% of accuracy. Sometimes we are not using the sigmoid, we are using ReLU, and ReLU is also very popular. One of the reasons that ReLU is better is sigmoid. Sometimes we have the issue of vanishing gradient. ReLU and usually don't have that. So and ReLU is popular as well. So that's why if we have using ReLU, sometimes we can get a better accuracy. This is the AlexNet, which is much more complicated. So basically, we have more layers of the, and sometimes we need to consider like different and 3 channels because, I mean, for the ImageNet, it's like colored image, so it has RGB, so it's a lot of like more complicated things. And for the AlexNet, it actually has like 8 layers, has about 60 million of parameters. That's a lot of parameters, and we have like 650,000 neurons. So we cannot train these things into CPUs. Instead, we have to using everything on GPUs. This will be give us like 100 times speed up, but still took weeks on it. I mean, ImageNet to do that. So basically, as AlexNet is, I mean, give out by. I'm a guy called Alex, has spent a lot of time trying to, so like implement these things on a GPU. So this is actually being the first modern neural network framework because actually being the first like neural network architectures to be implemented on GPU. Then the rest of the and the neural networks are always implemented on the GPUs. People never train everything on CPUs because this is way too slow to work on. Okay. So this idea actually started this kind of like a revolution in computer visions like many years ago. So this gives you a like fantastic introductions of what we're doing here. So another thing that people will ask or think about is what actually this kind of like convolution neural network actually learn, right? So so you think about it actually, this is like say the regions right here will actually and like think about the way and keep doing this convolutions on the images. We combine this like subregions, take the convolution and informations and apply it to this values. Then we take another convolutions of the subregions and to get like this single values right here. So basically this single values contains all the information of much larger images, right? So, and you can think about everything is like multi-scales, right? So this is like still tiny scale, but this is like medium scales. But at this level, after you apply multiple convolution layers, and the value here represent a very large portion of the images, right? So like give and a good information of that. So basically, you can think about like, and the receptive field of neuron is the input regions that can affect the neuron's output. The receptive field of the first layer is the neighbor, right? And depending the kernel size, it actually capture very local patterns, right? Because we're only interested in maybe 3x3 pixels, which is a very local patterns. But if we after we apply multiple layers of convolutions, we are working on like higher layer of neurons. And then this receptive fields can be much larger. It can capture much more global patterns. You can see right here, after maybe 2 or 3 layers, you can see they have like very weird patterns start to showing up. Actually to start to showing some patterns. That means each neurons on the higher layers, after you apply multiple layers of convolutions, it actually give you some global structures. They are looking at certain global structures of this image. They are trying to detect that kind of global structures in these images, right? So this is basically they are trying to looking for example, right here, they are looking for the honeycomb shape of the images to see whether they have any kind of like honeycomb shape. For example, right here, they probably looking for something like circles, like tires. For this one, it's probably the sun or something like this, or like a circle shiny version of the images, right? So, and you can give some ideas right here. So you can see this is my input images, but like gradually you can see after like couple layers of like the convolution neural network, it actually extract informations, right? For this like animals right here, actually for this ones, they're trying to extract certain like areas of the animal to extract the information about the animal and trying to suppress the environment, because the most important things to get the classification correct is we need to extract the object that we are interested in. Otherwise, like those background things should be automatically muted. In fact, this is how the convolution neural networks are doing. By tuning these parameters, it can shine out or like emphasize the weight of those animals instead of backgrounds. Right? So this is the most important part, what we are trying to do here. So in fact, we can feed those images in our neural network to see which one and would activate certain neurons. This is give you some idea. For example, this is like flowers here. It actually is unit sensitive to the white flowers. It actually capture those white colors. So this is also something like, like sensitive to round spiky flowers. So this is something that these neurons will be turned off. For example, right here, you can see these are like round spiky features we are trying to capture right here. So you can think about this is neuron is trying to see whether in these images that kind of patterns will show up or not. Right. So this is basically how a human being is trying to think about how to process these images. For this like honeycombs to see whether in these images, whether this honeycomb shapes are being show up or not. Right. So this is basically what it's doing in this convolutional neural networks. And also, so the most important thing is that we need to train in this convolutional neural network well and very efficiently. So the most important thing is we need to apply some like stochastic gradient descent to minimize the training error, and also we can also apply this backward propagations. This can be applied to convolution layers, pooling layers as well, to compute a gradient. Everything, and the most important things in neural networks is basically it has backward propagations properties that you can calculate the partial loss, partial parameters very efficiently through the computational graph. So basically, this is and through this packages, it can compute a gradient very efficiently. You don't need to actually using hand to compute this gradient anymore. But the problem is we have like millions of parameters need to fit. It's easy to overfit, and of course we need to come up with various different methods to process that. So this is something that we're going to talk about later of the lectures, maybe next week. All right, so this is convolutional neural network, and the next thing I want to talk about is how we implement these things. Right, so and this is actually I'm going to talk about the everything in the way that we're using the GPU. Sorry, the packages of PyTorch. I mean, it's very simple like packages. It's very similar to NumPy, but this is basically the things. This packages. It's automatically loaded in the Colab. You can just use that, and also Colab has GPUs. You can just using GPUs automatically. So this is very like handy, very convenient for everyone. So basically, this is basically loading all these packages. PyTorch is very, very popular. It's an open source deep learning platform, provide a very good and research is very easy to deployment. It's very easy to modify and so I'm going to show you how this is being done. And I mean, it's always a good idea if you don't know how to do it, you should Google that and maybe ask ChatGPT for a bunch of questions if you need it. So the first thing is say you already create an arrays in NumPy, you can simply so basically create like similar and things in tensors. So it's basically in NumPy, this is called array, but on the contrary, in the PyTorch, it's called tensor. It's basically the same thing. This will be the very basic building blocks. It's like NumPy's ND array, but you can also transform from like PyTorch to NumPy and NumPy to PyTorch. So this is torch dot from NumPy. It's like X NumPy. So basically, this is things you can transfer into PyTorch form, or you can have a PyTorch form to NumPy. It becomes .NumPy. So this bit, and it becomes like ND arrays. So you can do all these kind of very basic operations, plus and the norm. It's basically the same thing, and many functions already in NumPy are also in PyTorch. But you better to Google that to see whether PyTorch does support certain functions. If you want to apply the operation along the dimensions, in NumPy we're using axis. In PyTorch we're using dimensions. It's basically a different keyword for the argument. And the reshape a tensor, we usually using the dot view instead of reshape. NumPy we have a reshape, but in tensor we call it a view. It's slightly different way of that is this changes is actually passing by references. Is view actually return the references of the same tensors that the one pass in. That means if we modify the values, it will also change the values for the input. So you have to be careful of that. So for example, this is the like some random like tensors that we create full dimension like fourth order tensors here. So you see we have like 10,000 by 3 by 28 by 28. Then you can like dot view. That means I'm going to do it like n by c by 784. We know 28 times 28 is 784. All we can do is -1 c. So this means it's already automatically choose the first dimensions that we're getting. Right? Just tell you I'm going to reshape to c times 784. The first one, I'm not going to calculate that. You just calculate by yourself. But for example, right here, if you already do this things already, so like y equal to x dot view these things, you can see, and you can see this like shape is already being like and so reshaped by 784 right here. All right, so this actually shows you it actually is a passing by references. So I have a random tensor. I'm going to reshape to 1 by 16. If I actually modify the new tensor value, all right, so this like tensor value to -10 for the, like zeros entries, it actually see right here for this my old tensors, the value is also changed to -10, which is also 4 by 4, right? So I'm also of the 4 by 4, it actually being changed into -10. In fact, if you checked the pointer right here, they have the same values. So that means they have the same data storage pointer. So that means this is actually passing by references. The only difference is the shape is different, but the shape is although the shape is different, but the pointer is the same. They are like pointing to the same memories. Okay, so I think I will finish. Let's see. That's a lot of stuff. Okay, so let me just talk about one example here. Then okay, that's a bit late. It's almost okay. So and why not I stop here? So on the next lecture, we're going to talk about another very important stuff in the PyTorch, which is it's automatic and a gradient. So you can like PyTorch can calculate gradient automatically. It's very, very powerful, very, very useful in neural networks. So like such that you don't actually need to take derivatives by yourself. It just calculate all the derivative by yourself. Then you can just apply all sorts of different and optimization algorithm as you like. So this becomes very, very handy and helpful when we're training and tuning those like complicated neural network architectures. Okay, that's all for today. We will continue on the next lectures on all these programming like packages, PyTorches. That will be continue of the package discussions. All right.